between. Okay, so let me start with the definition of those objects. So firstly, the Calabi-Yau manifold is a projective manifold trivial canonical class. And there is the cohomological condition. So the cohomology of this structure is 0 for I is 0 to the dimension. Okay. So usually they call it, with this condition they call it Calabi-Yau manifold. So in this definition, the Calabi-Yau twofold is a KT surface, but usually they consider it higher dimensional one. Okay. So the example is in 2-dimension KT surface, algebraic K3 surface. And in 3-dimension, its most simple example is critic hypersurface in P4. Quintic 3/4. So it's adjunction formula. You can show that this has a trivial canonical class, and like let's say intersection of 3 quadric, like in P5, like let me see, intersection of degree 2 and degree 4. This is also Calabi-Yau. So, or you can consider some more complicated one, like in weighted projective space. 1, 1, 1, 1, 2. Yes. So here in degree 6 hypersurface, it's a smooth hypersurface, and this is Calabi-Yau. So and then you can consider some component intersection in toric variety. So most, yeah.
You allow singularities?
No, here this is singular, but in degree 6 case, this hypersurface is generally, it is smooth.
Oh, it's a hypersurface
inside?
inside
Here, with degree 5, 6. But if it depends on degree. If degree is the odd, then it's singular. But if degree is the even, then it is smooth in this case. Okay. Or you can think it like the majority example comes as component intersection in toric variety. So majority of example. Component intersection. Toric variety. So you know the projective space or the weighted projective space is already toric variety. Okay, and then like many, like 20,000 of examples, something like that, but it's still finite. Okay. So in this talk, I will explain some other construction of the Calabi. It's in toric construction, but in general we don't know.
Even when the dimension is free.
Dimension is 3.
No, free, arbitrarily high.
Arbitrarily high, but in that case we don't know. For fixed given dimension, we don't know there is infinitely many finitely many Calabi-Yau manifolds there.
But how about the peripheries?
It seems like also if you think about Calabi-Yau fourfold in some toric variety, the construction is very similar to this one in threefold case. So people still expect that there is in toric construction there is only finitely many,
Given dimension.
For given dimension. Even though the number would be very hard, huge, but still they think the finitely many. Yes, that's a big question. And okay, so but in Calabi-Yau manifold there is other definition. So you can define Calabi-Yau manifold as like this. So the Riemannian manifold. So other definition. Let's say compact manifold. SUN holonomy. So one can define Calabi-Yau manifold as a Riemannian manifold which has SUN as its holonomy group. So it has some. Okay. So in this case, in this respect, the Calabi-Yau threefold is in physics. There is a theory called the superstring theory. So this is a basis space for ten-dimensional superstring theory. So each 10 is like 4 plus 6. In physics, this is 4 is space and time, and 6 is the dimension of the Calabi-Yau. So in complex dimension, this is 3. So that's how they build it. And Calabi-Yau fourfold is supposed to is in physics. This is 11-dimensional. It's called M theory. This is the one of no, it's 12. Sorry, M theory, and this is F theory. So this is another kind of the physics theory in high energy, and this is the 12 is like 4 plus 8. So this is the real dimension, 8 dimension. So in complex dimension is 4. So like this. And between this one, this is the 10-dimensional, and this is 12-dimensional. There is also some physics theory called M theory that is 11-dimension. So that's that. In that one, so-called G2 manifold plays some role there. So is 11-dimension M theory. So this is 12 is that 11 is 4 plus 7. So here in G2 manifold is 7-dimensional. So it is odd. So it cannot be complex manifold. So this is real dimension, real manifold. So let me define G2 manifold. So G2 manifold is definition. Is 7-dimensional compact Riemannian manifold. There is a Lie group called G2, so with the G2 holonomy. Okay. So here in mathematics, it's G2 manifold and Calabi-Yau triple is totally different. This is complex manifold and this is just real manifold. And then this holonomy is very different. But in physics, the physicists claim that this higher dimensional theory should somehow contain some low dimensional theory. So somehow this G2 manifold, the M theory, somehow contains this superstring theory. So they claim that this G2 manifold, the geometry of this, the G2 manifold somehow contains geometry of Calabi-Yau threefold. But it's non-rigorous in mathematically. Okay. So, but in this lecture, I will construct this Calabi-Yau threefold and G2 manifold in very similar fashion. Okay. Okay. So also the as you questioned before, so one can ask that there is a finite or infinitely many manifold of G2 manifold or Calabi-Yau fourfold, Calabi-Yau threefold. The answer is not known. So I mean, generally for the manifold with special holonomy, there is no such result.
Again, you're speaking of fixed dimension.
Fixed dimension.
Oh yeah, threefold, fourfold.
Yeah, that's right.
So no,
Yeah. For each fixed dimension, there is example. But
they are continuous families, right?
yeah, they are continuous family. I mean, up to deformation. Yeah, there is only so far the constructed example only finitely many, so people don't know. And then also in physics theory, the physicists is also interested in that kind of question because, so in 80s they invented the superstring theory, and then they found that the basis space should be a Riemannian manifold with SU3 holonomy, and then they expected that such manifold just exists just unique, because then the theory is already determined. But if there is several Calabi-Yau threefold, then they need to choose which the Calabi-Yau threefold build our universe. So that's the initial expectation, but after that, many people constructed many other Calabi-Yau threefolds. So now, but still, there are finite many. So it's still a big question. Okay. So let me talk about the construction of Calabi-Yau manifold by deformation. Calabi-Yau threefold. By deformation. Okay. So we start with some normal crossing variety. So normal crossing. So let's say it's very simple one. So X0 is a normal crossing of two projective manifolds. So Y1, this Yi is all smooth. So this is a projective threefold. Let's say just smooth. Okay. And then you have two of them, and then they intersect some very specific way. So also, let's say D is Y1 intersect Y2, and this is surface, so smooth surface. Okay, and this Y1 and Y2 meet each other very specific way. So at here, so this is each of them is smooth, but the intersection at the point, that point is not smooth, but around the singularity of this one, locally the singular point looks like this one. So x1 x1 x2 equals to 0. So you see this is x1 times x2, so this is equivalent to x1 equal to, or x2 is 0. So this is, you can think it like 0, x2, x3, x4, let's say 0, no, x1, 0, x3, x4, like this one. So here, this is y1 correspond to this one, y2 correspond to this locally. Singularity is like, so each one is, and then they cross each other transversely. And then the intersection of these two things is like 0, 0, x3, x4. This is corresponding to the D, which is y1, y2. So, okay, so I will start with this kind of normal crossing variety, and then I will try to smooth it by deformation. So, there is two conditions. So, smoothing condition. So first one is this one. So this linear system contains D. Okay, so this D is a divisor on each y1 and y2, and then I require that they are anti-canonical section. Okay, and then I also require that this is a KT surface. So the second one is, this is called the semi-stability, so like this one. And so this is normal bundle of D inside Y1. Okay, so this is a line bundle, and this is a line bundle, and this is both of them is a line bundle on D, and you can take a tensor product. And then I require that this is trivial. I require that this is trivial bundle. So this condition called D semi-stability. Over D, yes. So this is, those are all the line bundle over D. Okay. So the gamma and Lamika proved this one. So here, it's gamma. Is proved this one. So this x0, this y1, y2 is smoothable too. Projective xt with kxt is 0. So what this means? So this means like so there is this one, like this map. So this is X is Kähler manifold. Kähler fourfold. So Kähler smooth fourfold. And there is a map like this one, and this is some disk on the complex plane. So this is, let's say, the such a map exists such that the central fiber, so pi inverse of 0 is x0, which is a singular one, and pi inverse of t, so t is not 0, is xt, is smooth. Okay, so there is such a map from the smooth Kähler manifold to a disk, such that the central fiber is this singular variety, and then the generic fiber is smooth one. Okay, so if we have this kind of map, then we call it this singular one is smoothable to some smooth this xt.
Can you say general things about this smoothability? Is it rare? Is it
rare? Is it really rare? Rare, that's right.
Are there other like general sufficient conditions or obstructions to
Ob-
smoothability in general?
Obstruction, there's many obstructions. So yeah, that's right. So usually, to me, it's smooth theorem for dimension 3. I think that it's the only one for 3-dimensional one. Yeah, it's a very rare thing. So here, so how in smoothing? So this is the formal one, but let's see how the singularity resolved in smooth process. So you see, so at the singularity is like this one locally, okay, and then so here you can this thing replaced by like this one. This is lambda and lambda equal to 0, okay, and then if you set lambda goes to some t which is not 0, then the variety resolved instantly. There is no singularity there. So locally, this is how the singularity resolved locally. Okay. Mm-hmm. So let me take an example. So let's consider P3. If you think about take the quartic hypersurface, smooth quartic hypersurface D. So this is a smooth quartic. So degree 4 hypersurface. This is actually KT surface. Okay. So you can for P3 you can choose a D here, and okay, then you can choose a smooth curve. So in this linear system, O of D and 4, so this is smooth. So on KT surface, you can choose this smooth curve and then blow up. So this is blow up Y2 P3, this is the blow up along C. Okay. So this is the P3, and this is the D, and there is some surface here C, and the curve, and then you blow up. You have the Y, and then if you consider proper transformation of D, then D does not change it because the blowing up center is inside in D. So in this case, it doesn't change it. So Y is still contain a copy of D. Okay. So here, so now So the first y1 is we need threefold y1 and y2. So first y1 is just y. And then this contains d, let's call it d1. And then also, the second one is also just y, and then it also contains a copy of d, so we call it d2. Okay? And then you attach this thing and this thing like this one. So x0 is like you choose this joint union of them and then paste it along this d1, d2. Because it has the same copy of it, and you can topologically paste it. And then you can show that this is a normal crossing structure. Okay, and then this thing is satisfy these two conditions. The first one is we start with D, quality smooth surface. So this is the anti-canonical section of P3, and then in blowing up, it does not ruin that property. So the copy of D is the anti-canonical section of this Y. Also, the first one is satisfied, and then here. Each of these normal bundles are all trivial, so all the condition is satisfied. So with this theorem, you can smooth this thing to some Calabi-Yau threefold. Okay, so x0 is smoothable. To xt. But we all know that kxt is 0, but by using some Clemens-Schmidt, some mixed Hatcher's structure theory, you can show that actually the 1 oxt, 2 oxt is 0. So you can show that. Okay, so we do these two conditions. This xt is smooth Calabi-Yau threefold. Okay, and then so you can calculate. That is the formula for Hodge numbers. The Hodge number is like this one. So h11 xt is 2. h12 xt is, let me see, 86. Okay. Also, you can. So this is you see, this means the rank of Picard group is 2. So this is three-dimensional thing. So there is a cubic form on this lattice. Also, there is a method for calculating cubic form on this one. So that we can. So it seems that this smooth method is very abstract, but actually you can calculate many property of this thing from this, the property of this one. So this is actually very not so bad construction. Okay. Okay. So this xt, for this Calabi-Yau threefold, the dimension of modular space is 86. Okay, so this situation is like this. So let's say this is the modular space of xt, so modular space. Okay, then there is the point in correspond to x0. Okay, so this is 86 dimension, and there is the hypersurface which contains x0, so which is the 85 dimension thing. So this is the 85 dimension. Okay. So if this point moves to some point inside this hypersurface, then this normal crossing stays as a normal crossing. So the singularity does not revolve. But if the point goes apart from this hypersurface, now that point corresponds to smooth Calabi-Yau threefold. So situation is exactly like this. Okay. So like xt. Okay. So here, I mean, so I said that there is a similarity of the construction of Calabi-Yau threefold and G2 manifold, but in this construction it doesn't see any such kind of similarity. So let me interpret this construction in some topological way, because this is a totally algebraic description of this construction. So let's turn to some topological interpretation. Okay. Okay, so so topological. Okay. So this condition 2 is implied like this one. So let d dy hat is like this one. So m d yi minus d. So what is this? So here, this one is a line bundle over d. So you can consider it as a manifold. You can consider this thing a threefold, three-dimensional manifold. And then this thing contains D, a copy of D. So you can just substitute this copy D. Okay? Then this is C star bundle. Over D. Okay? Then you can define a map. N star n hat dy1 to n hat dy2 by, so let's say x contains c star. So this is a fiber and y is on D goes to all over x y. So for locally, at least locally, you can consider this kind of map. And then this condition actually means that this map is globally well defined. You see, x goes to 1 over x. So this is, the boundary is kind of negative to each other. So that means this map is well defined. So you can make a global map like with this property. And with that map, so this is globally well defined. So condition 2 means globally. Okay. And so this is D is the divisor in YUI. So there is this property. So D has a neighborhood U I of D in YI such that UI is homeomorphic to homeomorphic to NPYI. Okay. So let UI hat is UI minus D. Because this is neighborhood, so you can subtract this one. Then, so now it's like this one. So here this map, so this is corresponded to N hat, topologically. And then you have a map pi this one to this one. So you have a map U1 hat to U2 hat. So with that one, we can make some topological construction. So that is like this one. So so yi is y1 minus yi minus d hat. So let w is y1 hat, the disjoint union y2 hat, and paste it. So u1 hat, u2 hat. Okay, so this one contains u1 hat, and this two contains u2 hat, and then there is by this homeomorphism, there is a homeomorphism between u1 and u2 because this is homeomorphic to this one. Okay, and then this is now this is compact threefold. Actually, not compact, not complex. This is a compact 6-dimensional manifold, but the point is W is homeomorphic to XT. XT is the Calabi-Yau we constructed before. So algebraically we can make it like a deformation, but in topologically we just from Y1 you can just subtract the anti-hierarchical section and then somehow topologically paste it. Then you have some compact Calabi-Yau threefold. Okay. So in some literature they call this thing non-compact Calabi-Yau. So this terminology is contradictory because the Calabi-Yau is already compact, but non-compact Calabi-Yau is. But anyway, they call it like this. Okay. So now let's turn to construction of G2 manifold. Okay. Okay, so we start with the same y and y2. Okay, so this is, but you know, this G2 manifold is 7-dimensional. So in this, at this time, there is, I mean, I think no one cannot expect how they related, but let me explain. So in G2 manifold, we need this condition, but the second one should be a little bit more stronger. So in G2 manifold case, we require this one. So we have 2 prime is like this one, and the y1 and the y2s are all trivial. Okay, so this is stronger than this one. Okay. So this is here we just require the tensor product term is trivial, but in construction of G2 manifold we require that they are individually trivial. Okay. Okay. Then, with this one, topologically, then this UI hat is isomorphic to just C star times D. Because the line model is trivial. Okay. Then, let's consider this one. So, yi prime is like this one. Y1 minus, no, yi minus ui. Okay, so this is the neighborhood of D, and then if you choose ui some specific way, then you can see this one. So boundary of it. So now this one has some manifold with boundary. So you can, the boundary is like this one. This is like let's say it's B. So this is homomorphic to S1 times D. So S1 times is a circle, real circle. Okay? It's because of this thing, you have this one.
So what is the
yi is, this one is still 3-dimensional. Because you, here, this is some open set in yi. So you just subtract the open set. Now this has some boundary thing. So this boundary is, let's say this is 5 dimension, 5 real dimension. Okay. Okay, then so now we define a map from this one. So psi P1 times S1, P2 times S2. So note that P1 itself has some factor of S1, but we still multiply another factor of S1. Okay, and the map is like defined like this one. So X1 is X1. So here you see. So this is now this is isomorphic to S1 times D times S1. Right? So the first coordinate is here, y is D here, and then Z is S1. And this one goes to Z, Y, X. You see? This is changed. So factor is X and Z is changed, and then this is well defined.
We want S1 at the end here, V2 times S1?
S1, yeah, sorry. X1. So now you have you construct a manifold. So this is M. It's like this one. So Y1 prime. So you have some disjoint union of these two things. And then paste it around B. So this is, oh no, sorry about that. Times S1. Y2 times S1. P. So here, so let me mark that this is homeomorphism. Obviously homeomorphism. This psi is homeomorphism. So B1 times S1, P2 times S1. Okay. So this thing contain this thing as a boundary, and this one contain this thing as a boundary. So I just pasted this one by this homeomorphism. Okay. Then this is a 7-dimensional compact manifold. Because this is in real dimension, this is 6 dimension, it times 1, this is 7-dimensional. And then the covalent show that here. So Alex A covalent. And admit a Riemannian metric with G2 holonomy. Okay. So now, I mean, our previous one, in the example, we prepare some y's, and then that y is specify this stronger condition, and then from that one, you can make a G2 manifold.
This is true for any smooth projective 3-fold y1 and y2, or for the particular example you have?
No. I mean, the example which satisfy those two conditions. And then there is some more technical condition, but it's more differential geometry. So it's hard to explain here.
It's very general result.
Yes, it's very general. Okay. So now they still searching for such a threefold. I mean, the most typical one is like for example y, you can make it from the blob of Fano threefold, but they are finitely many, and then they try to look at some Q-Fano threefold, but still they are also finitely many, and then so yeah, that's how story goes.
This theorem, what is the date? When was it proved?
That's 2003 or 2. Yeah, it's already old. Okay. So in this line of construction, the important thing is make an example of these yi's. Okay. So let's try to make some interesting yi. Okay. So let me explain briefly. So let's say this is the KT surface. And you can consider involution, non-symplectic involution. Yes. So this non-symplectic means like this one. So for KT surface, this one is C. This is one-dimensional. Okay? Then this law acts as the multiplication by -1. So this is A goes to -A. So with this property, we call it this sigma is non-symplectic involution. Okay? Okay. Then consider this map. So eta, so P1 to P1, this is like x, y goes to -xy. This is a very simple map. And then consider this one. So S times P1, and then quotient by this involution. So this is rho sigma and psi. So let's call it y hat. Okay, because this is the product of KT surface and P1. This is threefold, and you quotient it. But usually this is non-smooth. It has some singularity of a line, some curve, smooth curve. Okay, and then blow up. y hat y, this is blow up or singularity of y hat. Okay, and then one can show that after this blowing up, this y is a smooth one. So the fact is y is smooth, containing a copy of the original KT surface in its anti-canonical system. Okay. And this one, so KY restricted to S is trivial, or the equivalently NSY is trivial. So by adjunction formula, those are the equivalent. Okay, so this is, so here this is very good example of Y, because in KT case, there is many evolution of KT surface. Okay, so now this Y denoted like a SN rho, because it depends on KT surface and evolution of this sigma. Okay. So let's say there is two non-symplectic involutions, so rho 1 and rho 2 on the same KT surface. Then you can prepare Y S rho 1, Y S rho 2. Okay? And then you take a disjoint union of this one, and then this one contains a copy of S, and this one contains a copy of S. So you can just paste it. So you paste it. S. Okay? So this pair gives many Calabi-Yau threefold and G2 manifold. So in this, so this is goes to CYs and G2 manifold. So with these Y's, we construct with the Kovalov and I, we constructed more than 300 examples of G2 manifold. Okay. So in case of G2 manifold, there is a relatively small number of examples, which is constructed by Joyce, Dominic Joyce, and he constructed like around 200. And then we added more, 300 more. And then in his construct, he noticed that in his example, the Betti number, that's by this relation. Mod 4. So this is the Joyce's example. So the second and third Betti number, their sum is the 3 mod 4. Okay? But in our example, this is focus. This relation is not general. It seems that this relation just depends on his construction. Okay? So this is the end of today's lecture. So,